Welcome to G Fun Facts Online. In the vast expanse of the cosmos, where our minds struggle to grasp the sheer scale of distance and mass, nature has provided us with a remarkable tool. It's a phenomenon that acts like a cosmic magnifying glass, allowing us to see the unseeable and weigh the unweighable. This cosmic illusion, a direct consequence of one of the most brilliant ideas in human history, is known as gravitational lensing. Today, we're going to explore how this bending of light allows astronomers to put the universe's biggest monsters, supermassive black holes, on a cosmic scale. At the heart of this entire phenomenon is Albert Einstein's general theory of relativity, a revolutionary concept he unveiled in 1915. Before Einstein, we thought of gravity as a force, an invisible rope pulling objects toward each other, as described by Isaac Newton. But Einstein completely reimagined gravity. He proposed that it's not a force at all, but an intrinsic property of the universe itself. He described the universe as a four-dimensional fabric called space-time. According to his theory, massive objects don't just exist within this fabric. They actively warp and curve it. It is this curvature of space-time that we experience as gravity. The classic analogy is to imagine a bowling ball placed on a stretched rubber sheet. The heavy ball creates a deep depression in the sheet. If you then roll a smaller marble nearby, it won't travel in a straight line. Instead, its path will be deflected by the curve, causing it to circle the bowling ball. This is fundamentally how planets orbit the Sun. They aren't being pulled by a force. They are simply following the straightest possible path through the curved space-time created by the Sun's immense mass. But Einstein's theory made an even more radical prediction. If massive objects curve space-time, then everything that travels through space-time, including light, must follow these curves. This was a wild idea. Even Newton had pondered if gravity might affect light. But general relativity predicted a bending effect, twice as strong as anything Newtonian physics would suggest. This audacious prediction was put to the ultimate test in 1919 during a total solar eclipse. An expedition led by Sir Arthur Eddington traveled to locations in Brazil and off the coast of Africa. The eclipse was essential because it would block the sun's intense glare, allowing them to photograph the faint stars appearing right next to the sun's edge. The goal was to see if the apparent positions of these stars had shifted. And they had. The starlight passing by the sun was bent by its powerful gravity, making the stars appear slightly out of place, exactly as Einstein had predicted. This single observation electrified the scientific world and catapulted Einstein to global fame. The idea that gravity could act as a lens wasn't entirely new to Einstein. As early as 1912, he had considered that if a star, another massive object, and an observer on Earth were perfectly aligned, the intervening mass could bend the starlight in such a way that the observer would see multiple images of the distant star. However, he calculated the odds of seeing this effect from a single star and dismissed it as too improbable to ever be observed. For decades, gravitational lensing remained a theoretical curiosity. But in 1937, the brilliant and eccentric astronomer Fritz Zwicky made a crucial suggestion. He proposed that it wasn't just single stars that could act as lenses, but entire galaxies, or even massive clusters of galaxies. Their immense collective gravity would make the lensing effect far more significant and much more likely to be seen. The final piece of the puzzle fell into place with the discovery of quasars in the 1960s, extremely bright, distant objects that were perfect background light sources. Finally, in 1979, the theory became a reality. A team of astronomers discovered what they initially thought were two identical quasars sitting right next to each other in the sky. They called it the twin QSO. But upon closer inspection, they realized it wasn't two quasars at all. It was two images of a single quasar, its light being split and distorted by a massive galaxy situated directly between it and Earth. This discovery was a watershed moment. Gravitational lensing was no longer just a clever prediction. It was now a powerful, practical tool for exploring the universe. So how does this cosmic lens actually work? The mechanics are fascinating. When a massive object, like a galaxy or a cluster of galaxies, sits between us and a distant light source, it acts as the lens. As light from the background source travels towards us, it passes through the warped spacetime around the massive lens. This bending of light can create several incredible effects. First, it can cause magnification. Just like a glass lens, a gravitational lens can focus and amplify the light from the background object, making it appear brighter. This allows astronomers to study galaxies and other objects that would otherwise be too faint and too far away to detect, even with our most powerful telescopes. Second, it can create multiple images. As we saw with the twin QSO, the light can be bent along several different paths to our telescope, making us see 2, 3, 4, or even more images of the same exact object. And third, it can cause dramatic distortion. The images created by a gravitational lens are rarely perfect copies. They are often stretched, smeared, and twisted into bizarre shapes, like arcs or even complete rings. The specific appearance of the lensed image depends entirely on the mass of the lens and the precise alignment between the source, the lens, and us, the observers. When the lensing effect is very strong, it produces these spectacular, easily visible distortions. If the alignment is almost perfect and the lensing galaxy is relatively symmetrical, the light from the background source can be smeared into a complete circle. This stunning phenomenon is called an Einstein ring. The Hubble Space Telescope has captured breathtaking images of these cosmic halos, like the one created by the galaxy cluster GALE CLUSO 22058s, which is one of the most complete Einstein rings ever found. It looks like a glowing golden ring suspended in the blackness of space. More often, the alignment isn't perfect, or the lens is a lumpy, irregular cluster of galaxies. In these cases, the background light gets stretched and distorted into a series of bright, elongated arcs. A famous example is the galaxy cluster Abell 2218, where the immense gravity of the cluster warps the light from dozens of more distant galaxies into a mesmerizing web of thin, curving arcs scattered across the image. Perhaps the most iconic example of multiple images is the Einstein cross, where the gravity of a single foreground galaxy splits the light from a background quasar into 4 distinct points of light, forming a cross shape with the galaxy at its center. But not all lensing is this dramatic. Much more common is a phenomenon called weak lensing. This is a far more subtle effect, where the light from a distant galaxy is only slightly stretched or sheared by the gravity of foreground matter. The distortion of any single galaxy is usually too tiny to measure. However, by statistically analyzing the shapes of thousands upon thousands of galaxies in a patch of sky, astronomers can detect a faint, coherent pattern of alignment. This pattern reveals the presence and distribution of mass in the foreground, even mass that is completely invisible. This is how we map the distribution of dark matter, the mysterious substance that makes up about 85% of the matter in the universe, but doesn't emit any light. Weak lensing allows us to see the invisible scaffolding of the cosmos. And then there's microlensing. This happens when a much smaller object, like a single star or even a planet, passes in front of a more distant star. The gravity of this small lens briefly magnifies the light of the background star, causing it to brighten and then fade over a period of days or weeks. This temporary brightening is a powerful tool for discovering objects that are otherwise too small and dim to see, especially exoplanets orbiting distant stars. By analyzing the light curve of a microlensing event, we can even determine the mass of the lensing object. Now let's turn to one of the most exciting applications of this entire phenomenon: weighing supermassive black holes. These are the true behemoths of the universe. with masses millions or even billions of times that of our Sun. We believe they lurk at the center of nearly every large galaxy, including our own Milky Way. Their immense gravity dictates the movements of stars and gas in their host galaxies, and we think their growth is intimately tied to the evolution of the galaxies themselves. But measuring their mass directly is incredibly difficult. They are, by definition, black. They don't emit light. So how do you weigh something you can't see? Gravitational lensing provides a direct and elegant solution. The core principle is simple. The amount of light bending is directly proportional to the mass of the object causing the bending. More mass means more curvature of space-time, which means a greater deflection of light. By carefully measuring the distorted images produced by a gravitational lens, astronomers can work backward to calculate the mass of the lensing object with astonishing precision. The process works like this. First, astronomers have to find a suitable lensing system, which is a matter of cosmic luck. They need a bright, distant object like a quasar, whose light is being clearly lensed by a foreground galaxy. Next, using incredibly powerful instruments like the Hubble or James Webb Space Telescopes, they take detailed images of the system. They precisely measure the positions, brightness, and shapes of the multiple images or arcs. The real magic happens next, in computer models. Astronomers build a detailed model of the lensing galaxy, accounting for the mass of all its visible stars and gas. They then run simulations to see how that mass distribution would bend the light from the background quasar. They compare the simulated images to the real ones. But there's a missing piece: the supermassive black hole at the galaxy's center. They add a black hole to the center of their model and adjust its mass. They can then see how the black hole's gravity adds to the overall lensing effect. The mass of the black hole that makes the computer model perfectly reproduce the observed images is the correct mass. The gravity of the central black hole has a unique and distinguishable effect on the light rays that pass closest to the galactic center, allowing astronomers to untangle its mass from the much larger mass of the surrounding stars and dark matter. This method has been used to successfully weigh several supermassive black holes. In one landmark study, astronomers used the lensed images of a distant quasar to measure the mass of the black hole in the foreground galaxy. The precise configuration of the lensed images was so sensitive to the black hole's gravity that they could pin down its mass with incredible accuracy. These studies are building a census of black hole masses across the universe, providing vital data to test our theories of how galaxies form and evolve. Of course, this technique isn't without its challenges. Finding these perfectly aligned systems is rare, and accurately modeling the mass distribution of the lensing galaxy with its complex mix of stars, gas, and dark matter is a computationally intensive task. Despite these hurdles, the future is incredibly bright. The James Webb Space Telescope, with its unparalleled sensitivity and infrared vision, is opening a new golden age for studying lensing systems. And upcoming projects like the Vera C. Rubin Observatory will survey the entire sky over and over, promising to discover thousands of new gravitational lenses. This wealth of data will not only allow for more precise black hole measurements, but will also let us probe the environments around them in detail, testing the limits of Einstein's theories in the most extreme gravitational fields known to exist. Gravitational lensing is a stunning testament to the predictive power of science. What began as a theoretical note that Einstein himself thought was unobservable has blossomed into one of the most powerful tools in modern astrophysics. By harnessing the universe's own natural magnifying glasses, we are peering into the distant past, mapping invisible dark matter, and weighing the most enigmatic and powerful objects in creation. These warped, beautiful images are more than just cosmic illusions. They are windows into the very fabric of space-time itself.